This site offers no natural advantage. There is no bedrock near the surface.
The soil here is compacted sand. It compresses under load and recovers unevenly.
Before any structure exists, its geometry must be fixed relative to unstable ground.
At extreme height, force must be spread before it is resisted.
This footprint is not dictated by height. It is dictated by load dispersion. Material removal is required before material support can begin.
This excavation does not search for strength. It creates space for it.
Width matters more than depth at this stage. Stability comes from area.
There is no hard layer to anchor into. The structure must float its load.
This condition defines every structural decision that follows.
At the start of this project, the city had no vertical landmark defining its global identity. Horizontal growth increases distance, not capacity. Vertical growth concentrates both. The objective was not a tall building. The objective was a permanent reference point. This ambition had to operate within physical limits imposed by soil and climate.
Measurements taken now define tolerances that cannot be corrected later.
Wind is present before height exists. Its effects must be predicted in advance.
Millimeter-scale accuracy at ground level becomes meter-scale deviation at height.
Only after constraints are fully understood can preparation begin.
Steel arrives in standardized lengths. Its role is not strength, but force direction.
Each cut defines where stress will be allowed to travel.
Variation here multiplies upward. It is corrected before placement.
Spacing is fixed to control cracking once concrete hardens.
Once positioned, steel becomes inaccessible. Accuracy is mandatory.
This grid exists to spread load before it reaches the soil.
Concrete properties are defined before mixing begins. Strength is verified in advance. Failure is not tested at scale.
Strength is verified in advance. Failure is not tested at scale.
This is the final reversible moment.
No material moves forward without verification.
This is the irreversible transition. Liquid material becomes structural mass.
The reinforcement grid now defines how compressive force will be transferred.
Air voids reduced load-bearing capacity. They are removed immediately. Uniform thickness ensures even stress distribution once curing begins.
Temperature control governs curing speed and final strength.
Strength develops chemically, not visually. The core is constructed as a continuous vertical element.
Continuous pouring prevents cold joints between structural segments. At this moment, the building begins resisting gravity independently.
The core now governs every subsequent construction decision.
The slip form advances only when lower concrete reaches required strength. Vertical speed is limited by chemical reaction, not machinery.
Temperature directly affects curing rate and final compressive strength.
Pouring schedules adapt to climate to maintain material consistency.
Vertical pumping pressure increases with height and must remain continuous.
Any interruption risks segregation and blockage inside the line.
Structural priority shifts upward as height increases.
These walls resist shear forces induced by wind. Deviation accumulates rapidly at extreme height and must be corrected immediately.
At this stage, the core is the building's primary structural system.
Wall thickness reduces with height as axial load decreases. Surface defects indicate internal inconsistencies and are corrected immediately. Wind forces increase exponentially with height, not linearly.
These voids are structural interruptions, reinforced to preserve continuity.
Alignment correction becomes smaller but more frequent as height increases.
At this elevation, the core resists wind before any external system assists.
Continuous pumping prevents material separation inside the delivery line.
This marks the threshold where secondary systems can safely attach.
Once cured, lower sections act as a rigid spine supporting all subsequent height.
Uniform curing confirms predictable stress behavior under load. Measured performance is compared against predicted models continuously.
Controlled movement is expected. Rigidity alone would cause failure.
These junctions distribute dynamic loads into the core evenly.
Cranes climb because lateral lifting becomes inefficient at extreme height.
The core serves as both structure and construction platform.
Beyond this height, additional systems must share structural responsibility.
Beyond this height, additional systems must share structural responsibility.
The primary structural phase is complete.
The primary structural phase is complete.
Floor systems distribute occupancy loads into the primary core.
These connections must remain flexible under wind-induced movement.
The stepped profile disrupts wind flow and reduces vortex shedding.
Outriggers convert lateral forces into compressive resistance. Stiffness increases without excessive mass.
These levels house systems that support the entire structure above.
Elevator systems are installed progressively to manage vertical logistics.
The facade seals the structure from environmental exposure.
These anchors allow movement while maintaining weather resistance.
The structure transitions from skeleton to enclosed building.
Construction now proceeds in vertical layers, not sequences.
Temperature variation requires controlled movement at every connection.
These systems support environmental control at extreme height.
Vertical transport is limited by cable weight and shaft geometry.
Zoning reduces travel distance and energy demand.
Controlled flexibility prevents resonance under fluctuating wind loads.
These systems redistribute lateral forces back into the core.
The building now behaves as a unified structural system.
Interior work follows enclosure to maintain environmental stability. Structural construction transitions toward final completion. The structure now operates as designed. No further transformation occurs.
Vertical transport now functions continuously across extreme height. This height is usable because structural movement remains within tolerance.
Aerodynamic shaping reduces wind-induced resonance.
The structure now defines its environment, rather than responding to it. Mechanical systems maintain stable interior conditions despite external extremes. This height exceeded previous structural limits at the time of completion.
This structure represents a solved engineering problem.
Stability here is engineered, not assumed.
Height was not the objective. Control was.
Human occupancy confirms that structural movement remains imperceptible at ground level.
Continuous monitoring replaces assumption with measurement. Zoned vertical transport prevents system overload across height.
These setbacks reduce synchronized wind loading along the height. At this elevation, atmospheric conditions differ from ground-level assumptions.
Envelope performance protects interior systems from pressure differentials.
Structural behavior remains consistent across thermal cycles.
Systems at maximum height operate within the same tolerances as those below.
This outcome reflects controlled engineering, not excess.
Replication depends on location-specific constraints, not ambition.
Long-term maintenance is engineered into the structure from inception.
Long-term maintenance is engineered into the structure from inception.
Accessibility preserves system reliability over decades. Design tolerances are validated continuously, not assumed at completion. Threshold-based monitoring replaces periodic inspection.
Subsequent towers respond to constraints that this structure resolved.
Joint behavior remains consistent across the full height.
Operational systems adapt seamlessly across environmental cycles.
The structure redefines spatial scale at the regional level.
This is not excess. This is resolution.
The structure now operates as designed. No further transformation occurs.
Vertical transport now functions continuously across extreme height. This height is usable because structural movement remains within tolerance.
Aerodynamic shaping reduces wind-induced resonance.
The structure now defines its environment, rather than responding to it.
Mechanical systems maintain stable interior conditions despite external extremes.
This height exceeded previous structural limits at the time of completion.
This structure represents a solved engineering problem. Stability here is engineered, not assumed. Height was not the objective. Control was.
Human occupancy confirms that structural movement remains imperceptible at ground level.
Continuous monitoring replaces assumption with measurement. Zoned vertical transport prevents system overload across height.
These setbacks reduce synchronized wind loading along the height. At this elevation, atmospheric conditions differ from ground-level assumptions.
Envelope performance protects interior systems from pressure differentials.
Structural behavior remains consistent across thermal cycles.
Systems at maximum height operate within the same tolerances as those below.
This outcome reflects controlled engineering, not excess.
Replication depends on location-specific constraints, not ambition.
Long-term maintenance is engineered into the structure from inception.
Long-term maintenance is engineered into the structure from inception.
Accessibility preserves system reliability over decades. Design tolerances are validated continuously, not assumed at completion. Threshold-based monitoring replaces periodic inspection.
Subsequent towers respond to constraints that this structure resolved.
Joint behavior remains consistent across the full height.
Operational systems adapt seamlessly across environmental cycles.
This is not excess. This is resolution. Long-term performance confirms initial design assumptions. Design margins absorb environmental extremes without intervention.
Vertical continuity is preserved through all circulation systems.
Uppermost systems operate under the most extreme conditions.
follows the same structural logic as the building itself.
Operational stability persists regardless of diurnal cycle.
This structure no longer changes. It performs.
Load paths remain constant regardless of occupancy variation.
Urban scale now organizes itself around this structure.
Thermal expansion remains within engineered limits.
Pressure management prevents envelope fatigue over time. At maximum elevation, airflow behaves unpredictably without shaping. Damping systems reduce oscillation amplitude to acceptable thresholds. External variability does not alter internal performance.
Human
Distance does not reduce structural relevance. It confirms it.
Monitoring systems remain active even in the absence of excitation.
Rapid environmental changes remain within elastic response limits.
Energy dissipation occurs faster than human perception.
At this elevation, airflow separation defines design success.
Environmental motion no longer influences structural behavior.
At maximum height, reference disappears. Only performance remains.
Human equilibrium confirms engineering accuracy.
The structure has exited construction history and entered operational permanence.
Environmental variability has been fully absorbed.
At this point, only geometry remains.
Successful engineering is invisible to its users.
Height no longer signifies risk.
Motion has been engineered out of consequence.
Scale has exceeded comparison.
This process is complete.
End.